All right, so let's look at our lab number 8, which is on MOSFET device amplifiers and inverters built using a metal oxide semiconductor field effect transistor. In the last lab, we had seen bipolar junction transistor and amplifiers and an inverter made out of that particular device. So today we look at, in this particular lab, the metal oxide field effect transistor. And as we had said in ESC201, most of the circuits that are out there at the present time, they all realize using, 90% of them are realized using metal oxide field effect transistor. Now, before we can do our experiment with this particular device, we'll have to create a model in the microcap simulator. And because the models that are there in microcap, built-in models are not really suitable for what we are talking about. So we'll create our own model, which is sort of representative for a MOSFET with a channel length of about 0.6 micron. And so let's see how we can create a model of the MOSFET here. So what we're going to do is, let me create a new schematic page here. All right, so we have the symbol of the MOSFET here. So this is an NMOS, so let's select an NMOS transistor here. All right, so let's select this one here. And so the NMOS transistor, the moment you select, it will ask for a model. So what we are going to do is we are going to create our own model here, and we'll call it ESC201. And we are creating for N type, so we'll write N here, okay? All right, so we created that particular model. And but note that the model is, if you double click on it, all the parameters they've all been put 0 or some default value which are not really correct. So we'll have to enter the model parameters, and we'll tell you in a minute how to enter those model parameters that are there here. And note that it's a 4-terminal device, and there can be a confusion about so what we can do is, if you want to know which terminals are which, you can double click again, and you can have pin names here. All right, so do pin names here. When you click on that, when you enable that, so it shows you the upper terminal is drain, lower terminal is source, the middle terminal is body, and the gate here. Note that the arrow, when it is going in, it points to an NMOS transistor. Okay, so how do we create the proper model here? So what we're going to do is share this particular file here, this text file here, where we have given the model parameters for the NMOS model here and for the PMOS transistor here. So the way we will create is as follows. If you go back to the simulator and you click on the models here. So if you click on the model, it shows dot model ESC201N NMOS here, and it shows a bracket where you have to put all the parameters. So what you can do is you can go back to your text file and take all the parameters from here, starting from level equal to 1 here, right up to these parameters here, right? So you can copy them, and then we'll go back to our simulator and we're going to add those parameters here. Okay, so our model is ready. All right, so we can go back here and go back to our page here, and if you double click on it, you can see that all the parameters have been entered here. CJ, all the values that you see here. Now, in addition to that, you can make MOSFETs of different sizes, different width. The L of the MOSFET here, we can go back and see the length of the MOSFET that we have chosen. Width it has taken as 1.2 micron, and the length would be somewhere here, 0.6 microns. Okay, so we are not going to touch that 0.6 micron. We'll keep it as it is. But there are other parameters. For example, the width is also entered here. But along with the width, we need, for example, the area of the drain and the perimeter of the drain. So this you can get by clicking on value, and then again copy from here. Value W equal to 1.2. Copy these parameters here and go back here and then paste it here. Right, so we have width is 1.2 micron, area of the drain is 3.6, and perimeter of the drain here. All right, so those information are entered here. So that part is taken care of, and now our model is complete. Our model is complete, and we can go ahead and now use this particular model for various studying the device property, or for studying amplifiers, inverters, and all of those other things that we will see shortly here. And for an NMOS, most of the time the body would be connected. So you will take body here and take here. So this is how we normally connect. Body and source are connected together, right? So this is there here. And now this is a MOSFET that is ready for us to study. Similarly, if you want a P-type MOSFET, so we can select a P-type MOSFET. This is P-type MOSFET here. And we can call it ESC201P. So this is P-type here, and it creates that MOSFET here. We can go back and check in the model. It has created PMOS here. We can go back to copy all the parameters from here. So we copy all the parameters here and we paste it here. All right, so that is there. This part is done. And in addition to that, we go back and double click on this, and we will enter the value also. Value equal to, again, we'll copy from here. Okay, so we enter that also. Control V here. All right, so now this is done here, right? So that takes care of the PMOS here. Note that the arrow comes out here, so that's PMOS. And you can put in here pin names, so it will indicate which are the pins that are there here. So drain, body, source here. So normally in a PMOS, the current flows from source to drain. So what we'll do is, we can do this. Right, so this is a better one here. Source on the top and the drain at the bottom here. And the body is again connected to the source here. So we'll connect the body together. Right, and now so it's fine. So this is the source terminal, this is the drain terminal here, and this is the gate terminal here. So our PMOS is ready. So with this PMOS transistor, now we can make amplifiers, inverters, all of those other things, similarly with the NMOS here. Okay, so that's the first step. It's very important that in your microcap simulator you create these models, because in the quiz also these are the models that we will use here, right? So we'll, for example, in the quiz and other places, it would be written ESC201N, so which means the model that we have just created. Similarly, if this is the model, it will be ESC201P here, right? So it's important that all of you create the model that we have just indicated in your own microcap simulator, so that these models are available. And with these models now, we will study the device properties and the different kinds of circuits that are there here. Okay, so let's look at the first part here. So we have this N-channel MOSFET here, and the source and the body are both grounded here. We've applied a gate voltage and drain voltage here. So the first thing that we can do is study the characteristics of this particular MOSFET, which means the drain current with respect to gate to source voltage, the drain current here with respect to drain to source voltage. Note that the only current that flows is from drain to source here. So if you wish, you can see, for example, analysis dynamic DC, right? So that one, we can see what the currents are. So there's a current of 103 microamperes flowing here. There's no current into the gate, and there's no current in the body also, right? So the only current that flows is from drain to source here. And this current obviously varies with gate to source voltage. For example, if I change it to 2.5, well, the current increases. And similarly, so the maximum voltage that we will apply to our NMOS is 3.3 here. That's the limit for this particular technology, 3.3 volts, and anything below that here. So let's study the characteristics here. So we could study, for example, use DC simulation. And we could study, let's disable this, and let's look at ID, the drain current of the transistor, versus, for example, the gate to source voltage here. VGS, let's look at VGS of this transistor here, VGS here, and gate to source voltage, and we are varying from 3.3 to 0 to 0.01 here. So we can see how the drain current goes here, right? So this is the typical variation that you see here. This is how, and note that, so this is, note that we have applied a voltage of 3.3 to the drain voltage here. So let's skip that, 3.3 to the drain voltage, and the transistor is actually in saturation region. And that's why it is behaving almost like a square law. So above the threshold voltage is around 1. So above the threshold voltage, the transistor obeys a square law kind of a characteristics here. So this is what we see here. And if you wish, you can make the voltage very small to force the transistor in linear region, let's say 0.1. And then the transistor will work more like a linear here, right? So note that it varies linearly with gate to source voltage here. And this is where the threshold voltage is. Threshold voltage is right here at this particular point. Note that 1 volt here. And threshold voltage basically means that the transistor begins to carry significant current once the gate to source voltage crosses the threshold voltage here. Note that although it appears as if the current is 0 here or negligible here, the current is not really 0. You can see this more clearly if you put the Y scale on the log axis here. All right. Right, so the current goes like this here. So current drops, we can zoom in here. So the current drops exponentially here, right? The current is, note that a linear graph on a semi-log kind of a plot indicates the exponential variation. So threshold voltage is somewhere here. So we can see where the threshold voltage is 1 volt. So right here is the threshold voltage. Once you go below that, note that it starts to fall exponentially here and then becomes very, very small here. And this is some leakage current that is there in the device here, right? And this is above threshold. So above threshold, the current will vary either linearly if it's in linear region or as a square law if it is in saturation region. Below threshold, it drops exponentially here. Anyway, so those are the things that you can study. For ID, ID versus VG. We call that the transfer characteristics. The other thing that you can study is ID versus VDS, the output characteristics. So let's do that. All right, so let's not do it on the log scale. Let's do on a linear scale here. So this is the typical variation that you see here. So this is the linear part here. It starts off with linear and then becomes non-linear here. And this is the part which we call as the saturation. So this is the part where the drain current is independent of drain to source voltage, or almost independent of drain to source voltage here. And this is the part where the transistor acts like a voltage control current source. For example, we can do here stepping. We can step the gate to source voltage here, let's say from 1 to 3 with a step of 0.5. We could step it and then see what happens here. Let's run it here. Note that for different gate to source voltages, we have different current here. And that's why we call this as a voltage control current source. For a given gate to source voltage, here the gate to source voltage is 3, and it's like a current source here. Its value is independent of drain to source voltage. But the moment we change the gate voltage, the current changes also here. Here is 2.5, this is for 2, this is for 1.5. And note that for 1, the current becomes very small because it's a threshold voltage here. Right, so you can study this transfer characteristic. This is called output characteristics because drain is often the output terminal. So it's drain current versus drain to source voltage here. And so this is called the output characteristics. The previous one was the transfer characteristics here. So you can study that. If you wish, you can take this transistor out and put a PMOS transistor and then study its characteristics also in a similar manner. The other thing that we can do is we can take we are going to take this particular MOSFET and make an amplifier out of it. So a step in that direction is, in an amplifier, what happens is you have to bias the transistor in saturation region. So we've taken a MOSFET, we have applied a gate to source voltage of 2 volt, applied a drain to source voltage of 2 volt here. The transistor will be in saturation region. Note that the condition for saturation region is that the drain to source voltage, which is 2 here, should be larger than the gate to source voltage minus the threshold voltage. So VGS is 2 and threshold voltage is 1. So VGS minus VT is 1 and the drain to source voltage is 2, which is larger than 1. So the transistor is in saturation region. Once you bias the transistor in saturation region, then the transistor becomes capable of amplification. So for example, we've added another signal here, a small sinusoidal signal here, say 0.1 volt, 1 kilohertz. And we can see that what this sinusoidal signal will do, note that now the sum of both of these signals is applied to the gate here. So the sinusoidal signal will also cause the drain current to go up and down here in a sinusoidal manner. And we can see that by doing, for example, the transient simulation. So let's do the transient simulation. All right. So it shows us let's put the cursor here. So it shows us the current, the voltage here, 99.69, so 100 millivolt here. So that's the voltage at this particular node, and this is the value of the current at that particular point, 123.35 microamperes here. Right, so basically this is the sinusoidal amplitude of the sinusoidal drain current for the sinusoidal input gate voltage here. So in order to see it clearly, what we should do is we should subtract the DC current here. So before you do this simulation here, for example, so note that what we can do is we can see, for example, if we do dynamic DC here, so it tells us the current flowing here is 102 microamperes. So that's the normal DC current that is flowing here, right? So we have to subtract from the net current, the DC current of 102 microamperes, then only we will get the sinusoidal current here, right? So let's go back to our transient, and we have to subtract the 102 microamperes, so which is 102 E minus 6, right? So now we'll see. Okay, so now we have a better picture here, so we can now see what is happening here. So this is the so note that for the positive gate voltage, sinusoidal voltage here, we have a sinusoidal current of 21.39, and for the negative part here, we have a current which is slightly less here, 19.35 here, as compared to the positive. So that's because the transistor is nonlinear, and therefore the output drain current that you see here is nonlinear as compared to the input voltage, which is a perfect sinusoid here. Anyway, so from this data here, for example, from a data like this here, so you know the input gate voltage that you're applying, sinusoidal voltage, the change in gate voltage is 100 millivolt, the change in drain current is 21.4, and by dividing the two, you get an important parameter of the transistor, which is the transconductance, the change in drain current divided by change in gate voltage here, right? So that's something that you can get from this particular circuit here. And in the next one, what we can do is we can take this circuit here and add a resistor and construct a amplifier here. So that's what we have done here. So let's remove this. So note that we have taken a bias voltage of 2 volt, and we've added a drain resistance of 20k, supply voltage is 3.3. We're going to take the output at the drain, and now this whole thing acts like a common source amplifier. The source is grounded, input is applied to the gate, and the output is taken here. So that's a common source amplifier, and we can study the characteristics of this amplifier. For example, the gain would be V01 divided by V in 1. So we could do the AC analysis, right? So let's do the AC analysis, and we're looking at the amplitude of the output as a function of frequency. So note that when we do AC analysis, it's basically doing a small signal analysis, and in which by default what the simulator does, it assumes the value of the input to be 1 volt here. All right, so it doesn't really matter. It takes the whole circuit as linear, and one is primarily interested in the ratio here. So let me plot this out. So we get a gain of 11.97, so about 12 dBs is the gain here. 12 dB is the gain here, and to find the 3 dB frequency, we can go here Y, and 12 minus 3, so that makes it 9 dBs, and let's go here, right? So it goes left here, so it goes 9 dB. So the 3 dB frequency of our amplifier is 1.7 gigahertz here, right? So that's the amplifier in the in the small signal domain here. Next thing is what we can do is we can look at it in the transient analysis and look at how V01 is changing as a function of V in 1 here. So let's do that. Transient analysis. So what we'll do is we'll remove this and we'll look at V in 1 and V01. And what we are doing is subtracting the DC offset from the output. So the DC offset is 1.275. So we are doing that here. All right, so let's plot this out. Right, so this is what we get. The input is in blue here. So we have applied 100 millivolts input here. And you can see the gain. Let's look at the gain here. Right, so you can see here the input is 100 millivolt. The output is 353.107. So the gain is 35.3, right? The ratio of these two. And there's 180-degree phase shift. When the input is positive, the output is negative, and back, and so on and so forth here. The other thing that you can also see is that there's a non-linearity. Note that the sinusoid is perfect. So for example, we can go here, and so the sinusoid is perfect. Note that V in positive amplitude is 100 millivolt, negative amplitude is also 100 millivolt here. While the output, the negative amplitude is 353.107, the positive amplitude is 378. The two of them are different. And that's the point that we have been saying, that the amplifier is, because the transistor is a nonlinear element, and therefore the sinusoid, the signal that you feed in, comes out to be amplified, but it also a little bit distorted. And the distortion will increase with the voltage that we apply here. So we have applied 0.1 volt here. Right, so we have applied 0.1 volt here. So if you change, let's come out from here. Let's change it to 0.2, and you can see the distortion increasing here. So let's do the transient analysis again. And you will see the distortion. Note that it's heavily distorted here. Right, so you can see that occurring here. So these are the kind of things that you can study. And it's getting distorted here. Note that basically what is happening is that at this point the drain voltage is decreasing, right? So note that the net voltage at this point is equal to the DC voltage plus the AC voltage. So the voltage here is decreasing, and the transistor is going into a linear region here. And so for transistor to work as a proper amplifier, we need the transistor to continue to work in saturation region. So that's a problem that is occurring here. Now we could relieve that problem here. Suppose I change it here to maybe 10K. Let's see what happens here. Right, so now the sinusoid is much better here, right? But there will be some distortion anyway because of the non-linearity in the transistor here. Anyway, so those are you can study a common source amplifier, you can study the effect of bias, you can study the effect of this drain resistance here. Now, of course, we reduce it to 10K, but the gain would drop and all kinds of things would happen, okay? So those are the things that we can study here. The next thing we can do is we can make a inverter out of it. So we've taken a transistor, added a resistor here. So that's a very simple inverter here, which you can see by simply looking at, let's say, the dynamic DC if you do, and you can see its effect. You apply, all right, so let's go back to inverter. So you apply high voltage here, 3.3. The output is low, 0.176 volt here. You apply a 0 here, and the output will go high, right? So you know it's switching. 0, low value here will give you high here, and a high value here will give you a low here. And you can see it more clearly when you go towards what we call is a voltage transfer characteristics. So we can do a DC analysis again. And in this case, now what we are going to do is note that we are going to sweep V inverter here. So we'll go from 0 to 3.3, the maximum value here. Right, so DC limits V inverter here. So let's choose that V inverter here. And 3.3 to 0 to 0.01, and we are going to look at the output voltage V02. Okay, so let's run it here. So that's how an inverter works here. Note that for low values of input voltage here, the output voltage is high here, and then for again high here, the value is low here. And there's of course a switching, I mean there's a, this is the transition period here. All right, so you can study the inverter characteristics through this particular circuit here. And what you can also do is you can study the switching of the inverter, right? So here, for example, you have, you could connect a voltage here to switch it on. So for example, we could connect a voltage here and we'll apply a pulse. So let's remove the DC here, 0 to 3.3. And let's apply, because this is going to switch there's a fairly fast inverter. So let's put here some 10 picosecond here. Let's put a delay of 0 here. Pulse width of, let's put 1 nanosecond here. All right, so these are so we're going to go from 0 to 3.3, rise time of 10 picoseconds, and fall time also 10 picoseconds. Pulse width of 1 nanosecond and period of 2 nanoseconds. Okay, so we have this here, and we'll connect this to an inverter. And we have connected another inverter as a load for this particular inverter. Note that nobody makes just one gate, so you have one gate connected to the next and so on and so forth. So that's why, to make the simulation realistic, we've connected another inverter of the same kind as a load here. But we're going to look at V03 and V3 here, right? We'll see how the switching occurs here. So let's do the transient analysis. And now we are going to look at in nanosecond scale here, and maybe 10 pico here, 1 pico maybe. Well, let's say 10 pico, we'll see what happens here. And we're going to see V in 3 and V03. All right, so we'll see that here. So let's run it here. Okay, so let's see it for a little bit longer, 2 nanoseconds, so 4 nanoseconds here. All right, so that shows how the switching is occurring. Okay, so you can see clearly here. We can do also, we can enable the operating point. All right, here. So that's the switching occurring. So it goes from, when the input goes from 0 to 3.3, the output goes from 1 to 0 here, fairly fast. It switches here. But then when the input goes from 1 to 0 or 3.3 volt to 0 here, the output switches here, but it takes some time to switch here. Right, so that's the delay in the rise time is considerably higher as compared to the fall time here. So the circuit is pretty good in terms of switching back to the 0 state, while switching to the 1 state here, it is taking a fair bit of time here. Okay, and that of course depends on, so what is really happening is that there is a resistor here and is charging up the capacitors that are there in this particular transistor and in this particular transistor here. So we can make the switching faster by, for example, reducing the resistor here. So it's basically an RC time constant, and so we can see here, note that it switches faster here. Right, so all the gate delays at the are basically because of an RC time constant. There's some resistor and some capacitance is associated with the transistor which are getting charged and discharged here. So that's where you see the delay here. And the resistor is a fairly high resistor which is charging up the capacitance, so that's why the delay is large. While when this particular node has to go down to 0, the transistor causes the discharge, and the transistor provides a low resistance path, and that's why the discharge is faster here. Discharge takes place much faster here as compared to the rise here. And you may be wondering, why don't we reduce this value further? Now what happens is, as you reduce this value further, the value of the 0 point here, that's why we did the VTC here. So the 0 point here, so note, for example, so you can see it from the voltage transfer characteristics that the value when the output is supposed to be low, so that is no longer a very low value here. So that rises as you make the value of the resistor smaller here. So that's where the trade-offs are there in the design of this particular inverter here. All right, so one last thing that we can do is look at the inverter, which is the fundamental building block of almost all the circuits, digital circuits that are out there, which is the Cmos here. Where what has happened is that we have taken the NMOS, which is there here, and instead of a resistor, we have connected a PMOS here. And you have to be careful that you connect the PMOS properly. So let me put pin names here. So note that I have not connected properly here. The source should be at the top and the drain should be at the bottom here. So let me take out here, right, and connect it back here. So now it's connected properly here. Okay, similarly make sure the pins are correct here, so you can give the pin names here. So that's fine here. Drain at the top, source, body, gate here. So that's for the NMOS, and then this is for the PMOS here. And then you can study the Cmos inverter. Now, if it becomes confusing, you can remove the pin names once you're sure that you've connected it properly. We can remove it. And the Cmos inverter also, you know, when you apply 0 here, you get 3.3 high here. When you'll apply 3.3 here, so you get 0 there. You can get 0 at the output here. So that way it works like a regular inverter. But the advantage of it is that no current really flows in either of the stable states here. So when the output is 0, note that the output is 0 and the current is in picoamperes, negligible here. Similarly, when the output is high here, so let's put 0 here. So the output would be, let's do dynamic DC. So the output is right, the output is 3.3 high here, and there's no current flowing here. Again, current is in picoamperes here. So this circuit does not consume any power dissipation when the output is either low or the output is high here. It's only during the transition period then both the transistors are on and there's a direct path to the ground here, and this current is drawn, and then you get power dissipation. Anyway, so what you can do is you can study the static voltage transfer characteristics V04 versus V in 4. So we could do DC, and we'll study let's disable this. We are going to see the last one, and we are going to vary this value here, VCMOS1, okay? So DC limits VCMOS1 here, and 3.320, and same thing. Let's run it here, right? So it's note that you get a perfect 1 here, you get 3.3, perfect 1 here, and then you get a perfect 0 here, perfect 0 value here, and you get a very sharp transition from low to high here, right? Very sharp transition here, and it's almost like a perfect inverter. An ideal inverter would be high here and then abruptly going down to 0 here. So it almost looks like a perfect inverter, right? So that's what you get when you have a CMOS inverter. And you can study the power dissipation, power drawn from the supply, what happens as you change the value here from 0 to 3.3. If you wish, you can take one inverter and connect it to the next inverter and do something what we did here and study the delay of this particular inverter as well. All right, so we have a MOSFET, basic MOSFET. So study its characteristics, then look at an amplifier, common source amplifier, then an inverter, study its voltage transfer characteristics, study the transients associated with the inverter, and then you can construct a CMOS inverter here. And for all of those things, the first step is that you must create the models as we have indicated right in the beginning. And make sure those models are there in your simulator, they are stored in your simulator, because as we said, the assessment will be based on those particular models that are there. All right, so with this background, let's stop.